Welcome back to your Statistical Methods class. My name is Jacqueline Lashuga and I'm going to be your instructor for today. As always, we'll begin by reviewing some of the material that was covered on the last lecture. In the last lecture, we learned about the statistical concept of variability or dispersion. Both of these words mean the same thing, how much the scores in a group differ from their mean. As an example, we compare two histograms. This is one of the histograms. It shows rainfall per year over the past 120 years in a certain place. The mean for this distribution is 33 inches per year. This is the other histogram, showing rainfall in a different place. The mean for this distribution is also 33 inches per year. Even though the two distributions have exactly the same mean, they are much different from each other. In this place, the maximum rainfall one year was 61 inches. So in this year and some other years, rainfall was enormous and flooding occurred. In this same place, the minimum rainfall one year was 3 inches. That must have been a dry year, and the crops must have died in the field for a lack of water. We say that in this place, the rainfall had more variability. There were many years where the rainfall was far away from the mean of 33 inches. The variability in this place was much less. The maximum rainfall per year was 45 inches. That's a lot of rain, but not nearly as much as the 61-inch maximum in the other place. The minimum rainfall one year was 21 inches. That was lower than average, but a lot better than the 3-inch minimum in the other place. We say that this distribution has less variability. On average, the scores are closer to the average. They're not spread out as much. The histogram is narrower. So, as these examples show, even if two distributions have the same mean, they can still differ in an important way, their variability. The question is, how can we measure variability? That is, how do we measure how much scores in a distribution differ from their mean? Last time, we discussed two different ways that statisticians use to measure variability. These are the average distance from the mean and the standard deviation. They are very similar, and they both are trying to measure the typical distance the score differ from the mean. In the last lecture, we show how to calculate the average distance from the mean. You just calculate the distance from the mean for each raw score and then average these scores. We also show how to calculate the standard deviation, which was slightly more complicated. You must begin with the deviations. If you have the deviations, there are 3 steps to calculating the standard deviation. First, you square each deviation. Second, you average the square deviations, which is going to give you the mean square. And third, you calculate the square root of the mean square. This is going to give you your final answer for the standard deviation. In the last lecture, we also covered some important terminology. We learned that the standard deviation is also called the SD. We also learned other names for the mean square. It's abbreviated as MS. Psychologists usually call it the variance. In the last lecture, we also talked about the relationship of the standard deviation and the mean square. The standard deviation is the square root of the mean square, and the mean square is the standard deviation squared. Because variance is just another name for the mean square, everything I have just said about the mean square applies to the variance. That is, the standard deviation is the square root of the variance, and the variance is the standard deviation squared. We are about to go on to some new material. But before we do that, make sure that if you have any questions about any of the material we have covered up until this point, you email your instructor and ask. Now I'm going to discuss the first topic of today's lecture, and we're going to start by questioning what is the standard deviation good for? The standard deviation isn't just a number you calculate. It's an important idea with many uses. The standard deviation is one of the most important ideas you will learn in this class. The standard deviation might even be the most important idea and the most valuable tool developed by statisticians during the past 2 centuries. There are many reasons why the standard deviation is useful and important. I'm going to talk about 3 of these reasons. Here are the 3 most important uses for the standard deviation. First, it indicates the average or typical distance of scores from their own mean. Second, it's a measure of variability, dispersion, or spread in a distribution. And third, it's a yardstick that we can use to measure how much an individual differs from the average. I will discuss each one of these uses in detail. First, as you already know, the standard deviation tells us something important about the scores in a sample. It is the average distance of these scores from their own mean. Now, in the last lecture, you learned about the average distance from the mean, which is one way of calculating the average distance of scores from their mean. But the standard deviation is also an average distance. It just uses a different approach to calculating the average. Mathematicians and statisticians have several ways to calculate averages. You learn one of them in grade school, add up all the scores of individuals, and then divide by the number of individuals. But there are other ways to calculate an average. Each is a bit different from the others and gives slightly different results. Here are the 3 steps for calculating the standard deviation. The first step is to square all the deviations. Remember, the deviations are exactly the same as distances, except that the deviations have plus or negative signs to indicate if they are above or below the mean. So in this step, you are squaring the distances. After squaring the deviations or distances, the second step is to calculate the average of these squares, which we call the mean square. And the third step is to unsquare the mean square by taking its square root. That gives us the standard deviation. Notice that step 1 is the reverse of step 3. In step 1, we square the numbers. In step 3, we undo or reverse the squaring by taking the square root. So in a way, steps 1 and 3 are intended to cancel each other out. And once they have canceled each other out, we're left with the middle step, calculating an average. So the main point to understand is this. When you calculate the standard deviation, you're calculating a kind of average, the average distance. This isn't the method for calculating an average that you learn in grade school, and it isn't exactly the same as the method we use for calculating the average distance from the mean. But the averaging method used for the standard deviation works, and statisticians have found it is very useful. So when statisticians want to know the average distance from the mean, they usually use the standard deviation. Let's approach this question a second time. What is the standard deviation good for? The standard deviation is a measure of the spread or variability in a distribution. This is a graph of 3 normal density distributions represented by 3 normal curves. All 3 distributions have the same mean. What is the mean of this distribution? Go ahead and take a couple of seconds to look at this figure and identify the mean for each one of these distributions. If you guess 0, you are correct. 0 is at the center of each distribution. The mean of each distribution is 0, and because normal curves are symmetric, we know that the median of each distribution is also 0. But what is the area underneath each of these curves? Well, remember that I said these are density distributions. The area of a density histogram or a density distribution is always equal to what? 100. So all 3 of these distributions have the same mean, the same median, and the same area. But what makes them different is their spread of variability. This tall curve has a standard deviation of 0.5. This curve is very narrow from side to side, so we say it has very little spread. We can see that most individuals in this distribution had scores between -1 and +1. Only a few individuals had scored greater than 1 or less than -1. So the individuals in this distribution had little variability. That is, their scores were all pretty similar and close to the mean. Let's compare this second distribution. It's a standard deviation of 1. As you can see, this curve has more spread from side to side than the previous one. Also, the individual scores have more variability. They aren't all crowded up close to the mean. Most of them have scores between -2 and 2. Finally, let's compare this third curve with a standard deviation of 2. It has a lot more spread from side to side, and the scores of the individuals are much more variable. For instance, we have quite a few individuals with scores between 2 and 4, and the same number of individuals with scores between -2 and -4. By comparing these three distributions, we can see that the standard deviation tells us about the spread of a distribution and the variability of the individual scores. A small standard deviation indicates the distribution is narrow, has little spread, and that the individual scores have little variability. That is, the scores are not much different from the mean and not much different from each other. A large standard deviation indicates that the distribution is wider and has more spread, and that the individual scores have more variability. We are now ready to discuss the third use of the standard deviation, that is probably the most important one. The standard deviation is a very useful yardstick to measure how much an individual differs from the average. This is the same graph of children's IQ scores that we have seen before. This little pink line at the bottom is a yardstick. It is exactly 1 standard deviation long. In this distribution, the standard deviation of IQ scores is 15 IQ points, so the yardstick is exactly 15 IQ points long. So let's consider the children who have IQs of 115. How many standard deviations are they away from the mean? Using our yardstick, we can see that children with an IQ of 115 are exactly 1 standard deviation away from the mean in the positive direction. Are children with an IQ of 115 smarter than average, less smart than average, or above average? Well, if the average is 100 and 115 is a bigger number than 100, then we would say that these people are higher than average. Would you say that it is rare and unusual to have an IQ of 115? Well, we can say that it is more rare than having an IQ of 100, but it still seems like it's a common value of IQ based on the height of the bar graph. Now here are the children with an IQ of 130. Using our yardstick, how many standard deviations are these children from the mean? 2 of them, right? And are they in the positive or negative direction? We're still in the positive direction. Would you say that it's rare and unusual to have an IQ of 130? It seems that it's somewhat rare, right? And again, we can tell by the height of that bar. Less people have scored at the 130. And which one would you say is more rare? 115 or 130? Well, again, based on the heights of the bars, we know that 130 is more rare than having an IQ of 115. Here are children with an IQ of 145. How many standard deviations are they away from the mean? Well, it seems like this set of students are 3 standard deviations above the mean. Are they in the positive or negative direction? We're still in the positive direction. And would you say that it's rare and unusual to have an IQ of 145? Absolutely, right? So again, go ahead and look at the height of that bar. It is very low, almost non-existent, meaning that very few people score an IQ of 145. We are now going to start a new topic, which are Z-scores. and Z-scores are based on the idea of using the standard deviation as a yardstick. Z-scores are really important to this course and to all of its statistics. I said before that probably the most useful thing about the standard deviation is that it can be used as a yardstick. Z-scores are based on this idea. Let's go back to the children with an IQ of 150. Using our yardstick, we said that these children are exactly one standard deviation away from the mean in the positive direction, because 15 IQ points are equal to one standard deviation. We can also say that children with an IQ of 115 have a Z-score of 1. This Z-score tells us that an IQ of 115 is equivalent to being a distance of one standard deviation away from the mean. And because the Z-score is positive, this tells us that the children with an IQ of 115 are above the mean, exactly one standard deviation above the mean. Notice I have added a Z-score of 1 down here at the bottom, under an IQ of 115. This tells us that a Z-score of 1 is equivalent to a raw score of 115. Now, we'll consider children with an IQ of 130. What do you think the Z-score is for children with an IQ of 130? Take a couple of seconds and think about this. We say that children with an IQ of 130 have a Z-score of 2. This Z-score of 2 indicates that an IQ of 130 is equivalent to being a distance of 2 standard deviations away from the mean. The Z-score is positive, indicating that an IQ of 130 is above the mean. Here are children with an IQ of 145. What do you think their Z-score is? At this point, I think the pattern is pretty clear. A Z-score for an IQ of 145 would be equivalent to 3. Notice that I have been filling in the Z-scores here at the bottom as we went along. So we're creating a new scale. Now we come to something a little different. We're now considering children with an IQ of 85. What is the difference between these children than all the other children we have considered before? Right, so far we have been considering only children with IQ scores above the mean, but the children with an IQ of 85 are below the mean, and this will affect the Z-score. First, I have put a little yardstick to help you. How many standard deviations away from the mean are children with an IQ of 85? Correct. The children with an IQ of 85 are exactly one standard deviation away from the mean, but they are one standard deviation away in the negative direction. That is, the IQ scores are less than the mean. We say that these children have a Z-score of -1. The number 1 indicates that their IQ scores are one standard deviation from the mean, and the minus sign indicates that they are below the mean. When the raw score is below the mean, the Z-score is negative. Now we come to children with an IQ of 70. What do you think their Z-score is? An IQ of 70 is equivalent to a Z-score of -2. How about an IQ of 55? What is the equivalent Z-score? Correct, this would be a value of -3 for the Z-score. At this point, we have just about filled in the scale for Z-scores at the bottom of the histogram. But there is one Z-score missing. What is the Z-score that is equivalent to an IQ of 100? There are at least two ways you can figure out that Z equals 0. First, you can use the yardstick approach. The mean IQ score is 100. So the distance between the IQ score of 100 and the mean is 0 standard deviations. The second approach is to look at the scale down here that we have been making. It's a number line with entries from -3 to +3, and the missing number that belongs in the middle is clearly 0. The score at the mean, in this case 100, is always equivalent to a Z-score of 0. If you know that a person's raw score is at the mean, then you automatically know that your z-score is 0. So we have learned that a z-score indicates how far an individual's raw score is from the mean, as measured in standard deviations. And the sign of the z-score, plus or minus, indicates whether the raw score is above or below the mean. A positive z-score indicates the raw score is above the mean, and a negative z-score indicates that the raw score is below the mean. Now that we have two scales at the bottom of the histogram, we can use it to estimate the z-scores for raw IQ scores. So, for children with an IQ of 120, what do you estimate is the z-score more or less? We can tell by looking at the scales that the z-score of an IQ score of 120 must lie between 1.0 and 2.0. It looks like it's closer to 1.0 on the line, so we can estimate it's around 1.2 or 1.3 or somewhere in there. What about an IQ score of 90? Is the z-score going to be positive or negative? The z-score is definitely negative because the raw score of 90 is less than 100, which is the mean. Also, we know that the z-score of 90 must fall between two numbers, -1 and 0. We could guess that the z-score is something like 0.70 or -80, but that's just a rough estimate. We can use the scale at the bottom of the histogram to make rough estimates of z-scores. However, if we want precise z-scores, we usually have to use a formula. This is the formula. The z-score is always equal to the deviation divided by the standard deviation. It's like converting inches to feet. There are 12 inches in 1 foot. If you know somebody is 72 inches tall and you're asked how many feet that is, you just divide 72 by 12. The same idea works with standard deviations. In the example we have been using, let's say a child has an IQ of 130. That's 30 points above average. So the deviation for the child is going to be 30. Let's assume we know the standard deviation of IQ scores is 15. To find the child's z-score, we must divide 30 by 15. That is, we divide the deviation by the standard deviation. 30 divided by 15 is 2, so the child's z-score is 2. Here's another example. We're still talking about raw IQ scores with a mean of 100 and a standard deviation of 15. We want to know, what is the z-score for a raw IQ score of 115? First, we need the deviation, which is 15. Then we use a formula at the top to calculate the z-score. C is the deviation divided by the standard deviation. The deviation of 15 divided by the standard deviation of 15 is 1. So a raw score of 115 is equivalent to a z-score of 1. Now let's try it with a raw IQ score of 130. First, we need the deviation. The deviation is 30 because we subtracted the IQ raw score of 130 and the mean, which equals 100. But now we need to calculate the z-score. And for us to be able to do this, we are going to apply the formula that's here at the top. The z-score is equal to the deviation divided by the standard deviation. So our answer is a z-score of 2.0. Here are two more examples. Go ahead and calculate the deviations. The deviations are 0 and -30. Go ahead and take a couple more seconds and compute the z-scores for these values. The correct answers are 0 and -2. Remember that a raw score of 100 is at the mean, and if the raw score is at the mean, it's equivalent to a z-score of 0. Okay, we're going to do this one more time. There is something a little different about this too. Go ahead and calculate the deviations for raw scores of 120 and 90. And here are the deviations. We get 20 and -10. Before you calculate the z-scores, I want to warn you that they will involve decimal fractions. Z-scores are usually reported to the hundredths place. In other words, you should probably have two numbers to the right of the decimal point. Go ahead and do your calculations. Please notice that the z-scores are reported to the second decimal place. That is, there are two numbers to the right of the decimal point. There is one class exercise that you must complete as practice to calculate z-scores. Now, because this class is online and under these circumstances, you cannot work in teams, but you can still complete the assignment on your own. You can find this class exercise in the same folder where you located this lecture. You will find one file that has the class exercise, which is calculating the standard deviation and z-scores, and a different section where it describes the steps for calculating the standard deviation and the z-scores. The main purpose of this class exercise is to get you some practice in calculating the standard deviation and the z-scores. Again, because we don't actually have team members, if you have any issues or questions on how to calculate this, you can consult your handout or you can email me directly. This PowerPoint slide shows the handout you receive and need to fill out. It shows the raw scores, which are the ages of 5 different individuals. The first thing you need to do is to fill in the column marked deviations. But for you to be able to complete the deviations, you first have to calculate the sum and the mean of the raw scores. So go ahead and take a couple of seconds. If you haven't already done this, pause the video, compute the scores, and then come back. These are the correct answers. The mean value is 16 for this set of raw scores. And these are the correct answers for the deviations. One way to check that you have done these deviations correctly, you can calculate the sum and the mean. Go ahead and take a couple of seconds and get those numbers. The answer should be 0 for both. Remember that the sum and mean of the deviations should always be 0. If you get a number other than 0, it means there is a mistake somewhere and you should go back and check your work. Now remember that once we have the deviations, there are 3 steps to calculate the standard deviation. And the first step is to square those deviations. So go ahead and take a couple of seconds and calculate these numbers. These are the correct answers for those square deviations. Now the second step is to get the mean of the square deviations. So go ahead and take a couple of seconds to calculate these numbers. The correct answer should have been 180 and 36. Now we're one step away from getting our standard deviation, and that is that we need to get the square root of the mean of the square deviations, which in this case is 36. Go ahead and do that and come back to this video. Before I give you the answer for the standard deviation, go ahead and think about the name of this number. We said that this number is called the mean square. And what do we need to do to this number? Again, we need to take the square root of it to calculate the standard deviation. 6 is the correct answer for the standard deviation. We're really close to the end. You now need to calculate the z-scores. And how do you do that? You need to divide the column of deviations by the standard deviation of 6. Remember that when a deviation is positive, the z-score should be positive too. When the deviation is negative, then the z-score should be negative too. So go ahead, take a couple of seconds and complete these numbers. And here are the correct answers. Now, again, we want to double check our work, and we do this by calculating the sum and the mean of the 5 z-scores. If you get anything but 0, that means that there was a mistake somewhere and you need to go back and check your z-scores. And these are the correct answers for the sum and the mean of the z-scores. We have arrived to the end of this lecture. Please stay safe and I'll see you next time.